Alright, in this video, we're looking at these two functions, fn and fn hat. These take a finite set, as we see down here, A, and map it to a set of all possible sums of elements of A. In the first case, we range over all n tuples of indices. Again, I should mention the natural numbers for me are the set 1, 2, 3, etc., so positive integers. And I also use this notation bracket n for just the positive integers from 1 to n. And in this first case, n can range through all natural, little n can range through all natural numbers. In the second case, it only makes sense for n ranging from 1 to r, where r is the size of the set A, the cardinality, I mean. And in that second case, we're just ranging through all n subsets of indices. So we're taking all combinations. Let's look at an example. So if we start with the set 1, 3, 4, n equals 1 is going to be the set of sums of length 1, so it's just the set itself. N equal 2, well, we're going to get all sets, the set of all sums of length 2. 1 plus 1, for example, is 2. 1 plus 3 is 4. 3 plus 1 is 4, and so on. Same with n equals 3, it's the set of sums of length 3. And you could keep going. So an interesting question is, well, what is the union of all of these layers? Well, of course this is just going to be all natural numbers because we have 1 in our starting set. But perhaps more interestingly, okay, let's get rid of the 1. What is this? Well, it's basically all natural numbers. At least starting, you get every natural number starting from the LCM of 3 and 4, which is 12. And, so 12, before 12 maybe you can't get everything, but starting from 12 onward, you're going to get every natural number. Because 12 can be thought of as 4 plus 4 plus 4, but that's the same thing as 3 plus 3 plus 3 plus 3. And if you want to then get 13, you just take one of the 3's and replace it with a 4. And then how do you get 14? Well, you take another 3 and replace it with a 4. And so on. So you replace all of them, that you'll be at 16. And then you'll have 3 4's at that point, so you can replace them with 4 3's, and then bring one of those up to a 4, and so on. So that basically answers not only what you hit, but with what multiplicity. The only gadget affecting multiplicity is that you can trade 3 4's for 4 3's. Okay. Okay, and maybe there are other questions you could ask, but I'm not super interested in that question. Let's move on to the fn hat part. So if we do the same set, again, n equals 1 is the same. N equals 2, again, we're only looking at basically distinct sums, or sums of distinct elements, rather. So 1 plus 3 is going to get 4, 1 plus 4 is 5, and 3 plus 4 is 7. And that's it. For n equals 3, the sum of all 3 is 8. It's also worth noting we could have had n equals 0, giving us the singleton 0 for the empty sum. But that just is, I think, more bad than good, so I'm going to ignore that. Perhaps we should also think about what is the union of all the levels here. Well, it is 1 through 8 except for 2. We can't ever hit 2 in the second case. The motivation is sort of the following. It's like if I have a set of sticks, let's say, or measurement tools. Let's say I have 1, 2, and then 4. Well, then I can put the 1 and 2 together and effectively measure something of size 3. You could also subtract, you like by taking 4 minus the 1 and then also measure size 3. I just didn't do that here. But sort of the motivation is that you can at least build up to something of length 3 in this case. So maybe you're literally using sticks, okay, or something similar or analogous, like maybe this is some kind of like precision measurement tool where you have a thin metal piece of 1 millimeter length and then 2 millimeter and then 4. Well, you can actually measure 3 millimeter by just putting these together. Right, so to me it's a very simple practical problem, but disguised as this pure math problem. Anyway, let's just look at a few results. And I'm sure this is studied under some other name. I don't know what this would be called in the literature. I'm not really sure where to look. It's sort of hard to search these. If you just think of a concept like this, it's hard to search something, a function like this, right? So, but admittedly, I didn't even try. I know in the past trying this is very difficult. But I just wanted to look at a few things. So some observations just with the first function. 1, 2, and 3 I'm not going to prove. I think you could prove 1 with induction on n, and 2 and 3 just by set inclusion. I basically just wanted to see what happened to a simple collection of sets, arithmetic progressions in particular. So I wanted to know what happens to arithmetic progressions. And so that's what this theorem is doing here. I'm just proving what happens. So let's just look at 1, 2, and 3 quickly. 1 is just saying that fn of bracket m, well, it's just n plus 1 up to n. So certainly, if I take the 1 in this set and add it n times, I get n. If I take the m and add it m times, the m and add it n times, I get nm. And I get everything else with higher multiplicity. But it is worth checking that you actually get everything. Again, the multiplicities are perhaps a more interesting question. With 2, here I'm just scaling by natural number, so you scale every element, and this works out. 3, same thing if I just add beta to every element. It's equivalent to just adding n beta to every element of this larger set fna at the end. So let's just prove this theorem. So the theorem just says that if you throw in an arithmetic progression of difference or gap d, all you do is you multiply the first element by n, multiply the last element by n, and the gap is again d. So it's very simple to remember as well. It also is very intuitive, and it's probably what it should be, without even thinking too much. So we'll just do the proof very quickly. You can write A in this very convenient form, just a generic arithmetic progression. So you do decomposition. First line is exactly by 3 above. You can take out this A on every term. Remember to put the n multiplying the A. Factor the d out by 2. And then we know what happens to fn bracket k. Starts at n, goes to nk. Put everything together. Again, the first term is a plus d. So our first term in the output is n times that. And the last term is n times the last term of our input. And the gap is again d. So it works out. All right, the example. What is f5 of this arithmetic progression? First term times n is 15. Second term times n is 135. The gap is the same. Done. There's some other questions, obvious questions. What do you do? More structural questions. What is fn of a star b, for star being something like union? And how does it relate to fna and fnb? Maybe it's something like in 2 here, you have this inclusion. I'm not sure. And then maybe you can start to set up some analysis by defining a norm. I didn't really think through this. It's just something like that might be true and looks kind of like the triangle inequality. and also what happens with multiplicities, what happens in the limit, and so on. So let's move on instead to what I think is more interesting to me, that is, which is fn hat. So first I'm going to look at fn hat of this set, 1, 2, 4, 8. Same thing happens when we look at the layers. So the set of sums of length 1 is the same thing. N equals 2, set of sums of length 2. Again, these are unique sums, so there's at most 4 choose 2, which is 6 elements in this set, and there are exactly 6. So they're all hit exactly once, or all the sums here are unique. N equals 3, there could be at most 4 choose 3, which is 4 elements. There are exactly 4. And then there is, again, adding all of them together, which is necessarily unique. Again, we can't allow 0 in our starting set. Okay. So the interesting thing here, if you look through this, of course, the layers are just, what we're doing is counting in binary, right? So the n equals 2 layer are just the numbers when written in binary have 2 ones. N equals 3 layers, ones that have 3 ones, right? And so actually each number in bracket 15 appears exactly once, and it's sort of the most efficient way to generate those numbers. So in other words, going back to the motivating example, I can I can measure all the numbers 1 to 15 with just these 4 measurement sticks. Okay? So now f hat a, capital F hat of a, is just a union of these layers. So in this case, it's just bracket 15. Scroll down a little bit here. Shoot. There we go. So observation is, of course, if you go up to any power of 2, it partitions this set. Okay. I think we all see that. You can count in binary. So in other words, this 1, 2, 4, 8 is one of the nicest preimages of bracket 15 along capital F hat. So the question here, which I think is a nice central question to start off, is what else maps to bracket 15? So what else is in this preimage? F hat inverse bracket 15. And it's maybe a good idea to stop and think about this for a little bit. Is there anything else in here? Okay, it turns out there is, and it is bracket 5. So you might have noticed that 15 is a triangular number. So 1, 2, 3, 4, 5 add up to 15. And also, it is true, you can check that f hat of bracket 5 is bracket 15. And that is actually important to check. Once you check it, it's obvious, but it's worth checking once. So why? I mean, that's the interesting question. So why is it only these two things? For this example, it's basically because there can only be one thing of length 5 and one thing of length 4. Okay, so you could just look at all partitions of 15, in particular just the ones that are unique. So there's 27 unique ones, it turns out. Bracket 5 is the smallest one of length 5. So the argument is if you had anything else, so any A, B, C, D, E, let's say, of length 5, so something like that of length 5, the total sum of all the elements would be greater than 15. And we have to be a precise inverse of bracket 15. So we can't have anything larger if we map over across with f hat. So of course it's the only possible 5-element set in this preimage. If there's, on the other hand, a 4-element set, by the way, it should be clear that a 3-element set can't possibly be in the preimage because there would only be 7 possible sums. So we can only hit 7 numbers with a set of size 3. We need to hit 15 numbers. Turns out set of size 4, you can hit exactly 15 numbers. And that basically is the reason why. So you can read through the rest of this, but if you want. But effectively, the argument is that 1248 has only 15 possible sums, distinct sums that you can form, and you have to hit every number exactly once. So you have to be perfectly efficient. And the only 4 set that does that is this one. So these are the only 2 elements in this pre-image. So I'm interested in this inverse problem. So that's what we're going to look at the rest of the video. A few basic questions. I guess we'll lead up to one more question here, but of course, if you have a triangular number, f hat of bracket n is bracket Tn in general. And if you have a Mersenne number is one in the form 2 to the n minus 1, which 15 also is. So 15 is both Mersenne and triangular. Then you get this sort of power of 2 set in the pre-image. So 15 is both, and that maybe made this argument nice. So it might be worth looking for other numbers. What other numbers are both Mersenne and triangular? Kind of curiosity is that the next one is 4095, and actually it's the only other one. This was due to Nagel, where you can look up this Ramanujan-Nagel equation. So I guess the next question is, oh, maybe it's not so trivial. There might be more than just these 2 in this pre-image of 4095. So I don't know what that is. I'm sure it's very large actually. But question to you, see if you can find that. I'm sure you can write a computer program to find this, but can you say anything beyond that? Right, is perhaps the interesting part. Okay, so the last part is let's just solve this problem. So let's first think about a few things. To do any analysis here, I want to think about some size of a set. So I'm going to use 2 notions. The cardinality of a set is number of elements, and then the sum of the elements. Again, recall we're using natural numbers here, so these are all positive, or at least non-negative. So these actually do form a norm. Okay. This is just the L1 norm, by the way. But these are different ways of measuring things, right? The first one measures how many sticks I have, and the second measures how much material is used to make them. Regardless, if we want to find a solution that is nice to this inverse problem, we'd probably want to minimize all of the norms. In fact, another thing you could minimize is the largest element of our set. That's not something we're considering, but that is another thing you could consider. So let's just do one more motivating example before the end, theorem at the end. So consider finding a nice A such that f hat of A covers or includes bracket 20. So it just hits all the numbers 1 to 20. So you can, of course, just take A to be this power of 2 set, and that we know covers the numbers up to 31. Okay, but the sum of these elements is 31, so the L1 norm is quite large. We'd be using a lot of material. Let's just try something kind of forcing. So we'll scrap the 16. We'll leave 1, 2, 4, and 8 because that is sort of efficiently covering 1 through 16. But we'll add on the x here for some minimal x that still covers, so that the image still covers 1 through 20. Of course, 1 plus 2 plus 4 plus 8 is 15, so x has to be at least 5. But actually x equals 5, of course, works. So you can just, that's all we need to do. Now, if it turns out that x equals 4 worked, well, we'd have to bump it up to 5 because 4 is a power of 2, and we want A to be a set, not a multi-set. For just this video, I'm going to include that annoying technicality. Of course, in practice, just throw an extra 4 in there in that case. But Okay, here the point is the L1 norm is basically n, or basically the sizes that we want to cover. So, but yeah, the other thing I wanted to bring up, I'll bring it up one more time. So this sort of using the binary counting idea is like the most efficient way. It sort of minimizing this cardinality, but then throwing x in a minimal way also minimizes this L1 norm. So it minimizes both of these, but it doesn't do something like minimize the largest element, which is something I'm not really considering that you could perhaps consider. Like it, I haven't checked this, but what if I took the 8, bumped it down to 7, but took the 5 and to balance it out, I bumped that up to 6. Okay, I don't know, but conceivably that could still cover the numbers 1 through 20. You would have to check it. And now, if you were concerned about, making about minimizing the largest element, which is another way to measure the set, that would be a better solution. I'll let you check some of these things. Okay. The last theorem here is, okay, we'll read through it. Take n a natural number, take L to be floor of log base 2 of n. Then we have two cases. One, if n is Mersenne, just take all the powers of 2 up to 2 to the L. That'll be a solution to the inverse. Problem here, I think this is inverse image there. Yeah. Otherwise, let x be the largest number such that largest natural number greater than the remaining difference. Right, this part here is the sum of these elements. Actually, there's another mistake here. This should just be 2 to the L. Because, sorry, this is the sum of these elements. Yeah, okay, that's right. Which isn't a power of 2, just because we're talking about sets, not multi-sets. But that's kind of a meaningless thing. Then you could just tack on the x and it satisfies the covering problem. Or it's basically an inverse. Okay? And, okay, roughly what we're saying is that we have nice solutions. So the cardinality base is basically log base 2 of n, and the L1 norm, the sum of the elements is basically n. So these are very nice. And here, if this is confusing, I have some explicit examples with all the numbers here. Again, this column, we don't always get 1 just because of this weird issue with x not being a power of 2. But it should be 1, basically. So further questions, I kind of already alluded to these, but how do you improve this theorem? Okay, are there other special collections of sets so that we don't completely know the inverse image, but are there ones where, like arithmetic progressions or something, where you can completely determine the inverse image? Or, I don't know, can you just solve this in general? Maybe there already is. And how do multiplicities get involved? That's another good one. Which we didn't explicitly talk about. Alright, that's all I got.